Good morning, Math 150 students. Today is our last day of calculus, Math 150. The notes today go back to your first page of notes on what is calculus. And if you'll get your notes out that you had completed that day, and also a blank sheet of paper, as I add one more topic to these notes, and that topic is called L'Hopital's rule. In the notes, I'm referring to the page where it says limits part 1, and your graphing calculator was required. The idea limit of a function is what connects algebra and geometry to the mathematics of calculus. You have now finished your calculus course. And what I want to do is I want to go back and look at several of these examples, not all of them, but several of these examples that fit what's called L'Hopital's rule. In example number 1, we looked at the limit of the function of 3x squared minus x minus 2 all over x minus 1. And we explored it, realizing that the domain here is all real numbers except x cannot equal 1 because of the 0 you would get in the denominator. We graphed it using a table of values from the left and from the right. And we realized there was going to be a hole in our graph when x is equal to 1, but we didn't know what the y value was until we explored it in our tabular data. And so it appears that 4.997, 5.0003 appeared that the limit from the left and the right were exactly the same. So we said the limit as x approaches 1 was going to be 5. We algebraically factored our function, 3x plus 2 times x minus 1, reduced this function to an equation, which is the equation of a line that had a hole in it because of the domain restriction. And so we have 3x plus 2 that corresponds with the plotting of the points that we have here. Our y-intercept was at 0, 2. Our hole was at 0, 5. Well, now I want to talk to you about L'Hopital's rule. L'Hopital's rule works in certain limit situations. The limit as x approaches a of f over g, if you get 0 over 0, again, which is called indeterminate, or if you get infinity over infinity, L'Hopital's rule says what you can do is, instead of taking the limit of the original quotient, take the limit of the numerator's derivative and the denominator's derivative at that same x value. If you get a valid answer, that will be your solution. If you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule again. So let's go ahead and look at our very first function, 3x squared minus x minus 2 over x minus 1, and let's do a direct substitution. Let's go ahead, as x approaches 1, just substitute in our 1. So if we take 3 times 1 squared minus 1 minus 2 over 1 minus 1, you end up getting a 0 in the denominator, but you also end up getting a 0 in the numerator. That means L'Hopital's rule does apply. So if we want to use L'Hopital's rule, instead of going through the tabular data, instead of numerically, analytically using L'Hopital's rule, we just take the same limit as x approaches 1, but we're going to use the derivative, which now we are very good at the derivative. We've been studying the derivative all semester. The derivative of the 3x squared minus x minus 2, the derivative of the numerator should be 6x minus 1. The derivative of x minus 1, the denominator is 1. And now if we directly substitute in x is 1, we get 6 minus 1 in the numerator, which is 5. You get 1 in the denominator. So our answer comes out to be 5. which is what we got when we used our numerical method using our tables. We did it analytically. And now we have L'Hopital's rule giving us the same results. In looking at our second graph, our irrational fraction with fractions and numerators of a fraction, we looked at this graph, noting that x can't be 3 and x also can't be -1 because of zeros and denominators. And we decided to explore this as x was getting closer to 3 from the left and 3 from the right. And we got this lovely decimal -0.062515628891. And here a very similar decimal from the left and the right. We've got our tables here from our graphing calculator. On a whiteboard, I worked on the fraction itself, and then hopefully you transferred it to your notes. And this is the graph from my graphing calculator. There's a hole in the graph when x equals 3. But we weren't exactly sure where that hole was at. In fact, we really couldn't see it, but we knew it was there. We analytically then considered doing some algebra and getting a common denominator, multiplying by the reciprocal, canceling out a 3 minus x with an x minus 3. As long as you said x cannot be 3, I'm going to see a hole, just to make sure we're looking for that hole at x is 3. And then instead of taking the limit of the original function, we took the limit of our reduced function, substituted in, and got -1/16, which then put in the calculator, we realized was the same decimal that the table was giving us from the left and the right of -0.0625. But our real answer is -1/16. Are we allowed to use L'Hopital's rule on this? I'm not sure, so let's go ahead and look at this with L'Hopital's rule. When we directly substitute in x is 3, so I've got my function, I directly substitute in the 3, and remember when we do this, we don't write the limit anymore. You get 1/3 plus 1 minus 1/4. You get 1/4 minus 1/4 in the numerator and 3 minus 3 in the denominator, and you get 0/0, which is our indeterminate form that indicates that L'Hopital's rule can be used. Well, now this is a little more complicated to take the derivative of to use L'Hopital's rule. We're going to take the same limit as x approaches 3. We have to take the derivative of this quotient, and we could use the quotient rule here. Here's a constant to take the derivative of, and then we have an x minus 3. Remember, we take the derivative of the numerator and then the derivative of the denominator. We're not taking the derivative of the whole thing. According to L'Hopital's rule, where is it up here? You take the derivative of the numerator, the derivative of the denominator separately, and then go ahead and take the original limit. So what I'm going to do to use L'Hopital's rule, I think the easiest way for me to do this is to approach this quantity of x plus 1 to the -1 power, and then I'm going to take the derivative using the power rule. I'll put the -1 in front and then subtract 1 from the power. The derivative of this constant is 0, and the derivative of the denominator is 1. The chain rule applies here, but the derivative of the quantity here inside is just 1. So you could ignore that, but remember, that's what the chain rule is all about. If this was not an x plus 1, if it was a 3x plus 1, you would have to use the chain rule. Okay, now we're going to go ahead and do a direct substitution. Let's go ahead and put 3 into the problem. Oh, before I put 3 in, I decided, that negative exponent, I think I'll put it in the denominator where it belongs. Getting -1 over x plus 1 quantity squared. As x approaches 3, I just do a direct substitution of 3. 3 plus 1 is 4. 4 squared is 16. And that gives me the same value where our hole was located as did the analytical method here, and almost the same answer as our tabular data, our numerical data did here. So why couldn't we use L'Hopital's rule on our first test? Our first test, we didn't know what a derivative was. Some of you did try to use it on your homework, and I kept saying you can't use L'Hopital's rule yet because we haven't talked about derivatives. And so now that we have it, we can use it. But we're at the end of the semester when we're really not doing limits anymore. Okay, this piecewise function does not apply to L'Hopital's rule. Here's one, absolute value of x plus 3 over x plus 3. We graphed this and we looked at what happens as x approaches -3. And we discovered that the limit from the left and the right were not the same. Limit from the left was -1, limit from the right was +1. Does L'Hopital's rule apply in this particular case? Yes, it does. Well, let's go ahead and see. If we take the limit as x approaches -3 on this absolute value function, just substitute it in, you're going to get 0 over 0. And so L'Hopital's rule does apply. Question is, do you know how to take the derivative of the absolute value of the numerator? Well, try to remember that the absolute value is either the same or the opposite of this. The absolute value of a number is either positive or negative. It's distance from 0. And so in the numerator, its derivative would be plus or minus 1. The derivative of x minus 3 would be 1. If this were negative x plus 3, it would be -1. And of course, we get a 0 in the denominator. Now, this limit of 1 over 0 or -1 over 0 does not exist. Just like our limit from left and right did not exist here. 1 over x squared, L'Hopital's rule does not apply in this case because the numerator is never going to be 0, even though the denominator might be 0. Sine of x over x. Oh yes, sine of x over x. As x approaches 0, we got our very special limit of 1. Do you recall this? Nice graph. We explored this on the Stan the Can problem. We did this on homework more than once. We have the sine of x over x graphed from a graphing calculator, graphed from Google, very famous function. Well, if we directly substitute in, you'll get sine of 0 over 0, which is 0 over 0, which means L'Hopital's rule can't apply. Now that we know derivatives, in order to take the limit, instead of doing all this fancy work with numerical approach, graphical approach, and because there was no analytical approach to this one, there's no algebra we could do. If you just take the derivative of the sine, which is the cosine, derivative of the denominator, which is 1, and take this limit, you'll get our very famous answer of 1. What about sine x over x as x gets large without bound? We needed to do that in example 6. As x gets large without bound, you see what's happening to the function. We did not make a table on this, but we did. I don't think we made a table on this. But if you directly substitute in this particular problem, you get the sign of infinity over infinity. And the sign of infinity, you might say, well, I don't know what the sign of infinity is. Well, it's somewhere between -1 and +1. It could be 1/2. I mean, it depends on how far I go on my angle. Infinity is just a large angle right here. And so the sign of a large angle, I mean, it can be anywhere between -1 and 1. And infinity in the denominator is just a very large number. I have infinity up here anywhere. I'll put pi temporarily, and I'll go replace pi with symbol of infinity as soon as I find it. So while you might have infinity in the denominator, you do not have infinity in the numerator. So L'Hopital's rule cannot be applied in this particular case. It's very, you're going to see when you get to Calc 2 that Calc 2 instructors don't like you really substituting in infinity because it's such a, the notation is just like kind of makes us feel like squeaking across a chalkboard, if you've ever had that feeling. We had sine of 2 pi over x. I do not believe in that particular case that L'Hopital's rule will apply. Then we did some group work. I had you try these problems of x to the third power plus 8 over x plus 2. And then we did group work 2, and then one more problem. Well, does L'Hopital's rule apply? Sometimes it does, and sometimes it doesn't. In this particular case, we did this, and actually I have the solutions here. We did it numerically. We substituted in values very close to the denominators x equals -2. We substituted in from the left and the right. It appeared that our limit was going to be 12. And then we remembered, gently prodded to try to remember how to factor a sum of 2 cubes so that we could analytically come up with the same answer. And we did. We ended up getting a parabola with a hole in it when x was -2 and y was 12. If we directly substituted in -2 to begin with, you get -8 plus 8 over -2 plus 2, which is 0 over 0, which is indeterminate. But L'Hopital's rule says we can we can determine the answer if we take the derivative of the numerator and the derivative of the denominator. The derivative of x cubed plus 8 is 3x squared plus 0. The derivative of the denominator is just going to be 1 plus 0, or 1. We take the same limit now as x approaches -2, and you get 12. L'Hopital's rule is pretty cool if you know how to take a derivative, and if L'Hopital's rule applies. It didn't apply to the tangent function, doesn't apply to this piecewise function, but the last problem that we did in your notes, and I've got an extra problem here for us to do, but the last problem in our notes was, I'm going to do on a whiteboard. It's x plus h squared minus x squared all over h as h approaches 0. So back on day one, not knowing that we have L'Hopital's rule, we struggled with these limits for a short while. We're going to look at the numerator of x plus h, and we're going to square it. And when we multiply that out twice, we get x squared plus 1hx plus another hx. And we also get an h squared. The numerators, x squareds, cancel out. I'm able to factor out a greatest common factor of h from the numerator. I cancel this out and say, well, h can't be 0. I'm going to see a hole in this graph. Now I'm going to directly substitute in, now that our domain restriction is removed. And realizing that as h approaches 0, this is going to be h. And 2x doesn't change. So our final answer was 2x. That's the old way of doing it, the analytical way. Well, now let's see if L'Hopital's rule applies. Let's go ahead and directly substitute h is 0 into our problem. As h approaches 0, we're going to go ahead and let this become 0. So I don't write the limit anymore. In the numerator, we'll get x squared minus x squared, which is 0, and the denominator, of course, is 0. And since this is indeterminate form, L'Hopital's rule does apply. We have to be able to take the derivative of this quantity, though. Since I'm running out of room, I'll just erase that. And now I'm going to take the limit of the derivative of the numerator and the derivative of the denominator, but I'm taking it with respect to h. H is approaching 0. Not with respect to x, but with respect to h. The derivative of h in the denominator here will be 1. The derivative of this with respect to h is going to be 2. The power of 2 goes down in front, x plus h. This will be to the first power as I subtract 1. Then I take the derivative of the numerator. And remember, I'm taking the derivative with respect to h, although in this case it doesn't matter. Not with respect to x, but with respect to h, my chain rule says it's times 1. And the derivative of x squared with respect to h is 0. It's not 2x. It's 0. Remember how I always said notation and make sure that you always respect your variables. So as h approaches 0, I'm going to clean this up a little bit. The numerator is just 2 times x plus h. And the denominator is 1. As h approaches 0 here, I can directly substitute for that and get 2 times x plus 0, which is 2x. Which one's easier? Is it easier to go ahead and do the algebra here and do it analytically and multiply this out and cancel? Or is it easier to take the derivative with respect to another variable? Kind of depends on who you are and how well you understand taking the derivative with respect to a variable. We're going to now do the extra problem that I have on your notes. So you can get another piece of paper out if you'd like. And here is the last problem I want to look at. The limit as x approaches 3 of x squared minus 8x plus 15 over 3x squared minus 9x, which I do not have done on this notes. So let's say that this is on a test. Perhaps this was on a test earlier, and maybe it was, maybe it wasn't. But let's look at this particular problem both ways. We're going to do it with respect to our old technique of the analytical method that will use L'Hopital's rule if L'Hopital's rule applies. We'll do this on a whiteboard. X squared minus 8x plus 15, 3x squared minus 9x as x approaches 3. So we have the limit as x approaches 3. Numerator is x squared minus 8x plus 15. I'm going to try to factor that quadratic. And the denominator 3x squared minus 9x, which I'm also going to try to factor. So the limit as x approaches 3. Factoring the first and then the last product of sum. We have x times x for x squared. Our favorite factors for 15 are -5 times -3. Multiplying and distributing out your outers and your inners, you get the middle term. The denominator, to factor this quadratic because that is an x squared, I'm going to factor by using the greatest common factor of 3x quantity x minus 3. Just like in our limit test, these have factors that are exactly the same. X cannot be 3. I'm going to see a hole here in my graph. If I were to graph this, I would see a hole in this graph. I'm not going to graph it. You take the limit of our reduced function. We substitute in. And again, when we substitute, we do not write the limit anymore. I'm getting -2/9. Well, since this is on the L'Hopital's notes, it probably means that L'Hopital's rule applies here. But let's look at the original function and do a direct substitution. See if we get 0/0. And again, we didn't have any notes in here where we actually had infinity over infinity, but infinity over infinity is another limit where L'Hopital's rule applies. We just didn't happen to have any in these notes. If we directly substitute in 3, we get 3 squared minus 8 times 3 plus 15. And in the denominator, we get 3 times 3 squared minus 9 times 3. So we have 9 minus 24, which is -15 plus 15. We have 27 minus 27. So we could actually go ahead and use L'Hopital's rule in this particular situation instead of doing our algebra, as long as we know how to take the derivative of the numerator and denominator separately. With respect to x, the derivative of x squared minus 8x plus 15 is going to be 2x minus 8. The derivative of the denominator will be 9x minus 9. So what I now have to do is I have to hope that I did this right. Direct substituting, x is 3, we get 2 times 3. Get 9 times 3, which is 27 minus 9. (27 minus 9 is 18. Which is -1/9. Okay, now this answer is not the same. So what I have to do is I have to go back, and you have to go back, and we have to go figure out what did Comey do wrong. X squared minus 8x plus 15 over 3x squared minus 9x can't have 2 different answers. Did we factor this correctly? Yes. X minus 5 times x minus 3. Did I factor the denominator correctly? 3x times x is 3x squared. 3x times -3 is -9x. Cancel this. X cannot be 3. I'm supposed to see a whole. Substituting in, 3 minus 5 is -2, and 3 times 3 is 9. Well, since it looks like my algebra is good, something must have gone wrong with my calculus or my substitution here. Did I really get 0/0? Does L'Hopital's rule really apply? Yes. So I must have taken my derivative wrong. Derivative of x squared is 2x, derivative of -8x is -8, that's right. Derivative of 15 is 0. However, the derivative here should not have been 9x. And if we were in class, you would have stopped me and said, call me, derivative of 3x squared is not 9x. But every once in a while, we need a fail-safe, and we, can lose our way. The derivative of 3x squared here should not be 9x, but it should be 6x. So sometimes when you're taking a quiz or you're taking a test and you go, you know what, I don't think this is working out. I've got to go back and check my work. sometimes it's almost easier just to go back and start the problem all over again rather than to try to find your mistake. Sometimes. I believe the derivative of negative 9x was correct. Now I've got 6 times 3, which is 18. And 18 minus 9, which is 9. So I had to make sure I could take the derivative of the numerator and the denominator. My algebra actually wasn't too bad. The derivatives weren't too bad either. Get the same answer. L'Hopital's rule. So that's it for our last lecture of the day. Lecture of the semester. I hope you enjoyed L'Hopital's rule. See you for the final. Bye now.